Hi everyone, welcome back to Synthesis Workshop. I'm your host, Caesar, and today we're joined by Dr. Aitor Maestro for an introduction to non-covalent organocatalysis. Dr. Maestro is a postdoctoral fellow at the University of the Basque Country where he develops recyclable asymmetric organocatalysts. Thank you for joining us.
Thank you for the kind introduction and welcome everyone to the second episode about asymmetric organocatalysis. In the previous episode, we went through the most relevant examples of organocatalysts activating the substrate through covalent bonding. Today, we will have an overview of non-covalent organocatalysts such as phase transfer catalyst, chiral Bronsted bases, anion binding catalyst, and chiral Bronsted acids. First, we will see the most relevant examples of chiral phase transfer catalysts based on quaternary ammonium salts and some key aspects on their historical development. In 1984, researchers at Merck published a groundbreaking example of an antiselective alpha alkylation of ketones. This report represents the first catalytic and highly antiselective example using a chiral phase transfer catalyst. The temperatures in the reaction were limited to those above the freezing point of the aqueous phase, but even with that, an antiselectivities up to a 92% were obtained. Doolin and co-workers observed a limited solubility of the catalyst in both phases, making the understanding of the reaction mechanisms highly challenging. According to the report, treating the catalyst with a strong base favors the catalyst dissociation into water-soluble species. A combination of those water-soluble species seems to form toluene-soluble heterodimers as the true catalyst for the reaction. Having this information in hand, the most plausible explanation for the high Anion control consists of an enol formation in the presence of the catalyst dimer. Intramolecular interactions between the catalyst and the substrate such as PP stacking may favor the ref phase attack of the enolate to the methyl chloride. The next key development on the design of chiral quaternary ammonium salts came more than a decade after the initial report by Merck. Chiral phase transfer catalysts were stopped for more than a decade due to the impossibility to access an antiselectivities above 90% in a general way. In 1997, LIGO and Corey independently broke this barrier by modifying the benzyl group on the ammonium salt. Both of them tested the reaction towards the antiselective alkylation of glycine ester derivatives, and the main difference between their catalyst was the substituent on the alcohol. LIGO used the unprotected alcohol as the catalyst. However, the basic reaction conditions and the presence of large amounts of alkyl halides as the electrophile result in the in situ formation of slightly different modified catalyst for each reaction. Also, the nature of the substituent on the alcohol did not drastically affect the antiselectivity. In contrast, Corey and co-workers used a protected alcohol in order to have a more consistent catalytic system. As in the previous reaction, a complex catalytic pathway was proposed. The solubility of anthracene substitute phase transfer catalyst in the organic phase was slightly higher in this case, and therefore the main proposed role for the aqueous basic phase is the initial formation of the glycine ester enolate. The enolate is then transferred back into the organic phase with a chiral ammonium salt as the counterion, while the inorganic salts are dissolved into the aqueous phase. To justify the origin of Ondian antiselectivity, Corey proposed an explanation based on 4 quadrants. 3 of them are sterically blocked by the quinoklidine, quinoline, and anthracene moieties of the catalyst. This explanation leaves a single quadrant with enough space for binding the substrate, ensuring high Anion control. Another key aspect of this report by Corey and co-workers was the use of cesium hydroxide monohydrate as the base to minimize the amount of water in the reaction, allowing temperatures below the freezing point of the typical aqueous solutions. The combination of a new catalyst and lower temperatures result in an antiselectivities up to 99%. A few years later, Marbocco and Shibasaki reported efficient phase transfer catalysts based on other chiral scaffolds such as binaftil and tartaric acid derivatives, and tested them towards the alkylation of glycine esters. In particular, the catalyst reported by Marbocco allowed to obtain an antiselectivities up to 96%, even decreasing the catalyst loading down to 1%. More recently, these catalysts have also been used for other types of reactions, such as the 1,2 addition of glycine esters to aldehydes and imines. Just to mention a few other applications, Marboca reported in 2002 the enantioselective Asa-Darcel reaction, while Liang used a cinchona alkaloid-derived phase transfer catalyst in the enantioselective epoxidation of enones. In fact, the catalyst reported by Marboca and Shibasaki, along with the cinchona alkaloid derivatives appearing in the anthracyl group, are some of the most commonly used chiral phase transfer catalysts, even more than 20 years after the initial reports. Moving to Bronsted-based organocatalysts, some seminal examples were reported by Wimberg back in the 70s, using cinchona alkaloids as chiral catalysts. The initial addition of 1,3-dicarbonyl compounds and nitroderivatives catalyzed by simple alkaloids served as inspiration for many researchers several years later. Remarkably, even though most organocatalytic reactions reported in the late 90s and beginning of the 21st century required catalyst loadings ranging from 5 to 20%, Wimberg's early reports used catalyst loadings below 5%. As a practical example, they reported the organocatalytic synthesis of malic acid with enantioselectivities up to 98%. Cinchona alkaloids may act as bifunctional catalysts using the quinoklidine moiety as a base and the alcohol as a weak Bronsted acid to activate the electrophile. However, one of the most relevant bifunctional Bronsted bases was reported by Takemoto in 2003 for the enantioselective Michael addition of malonates to nitroalkenes. This catalyst combines a chiral tertiary amine with a thiourea moiety as a weak hydrogen donor to activate the electrophile in a more efficient way than the alcohol used by Wimberg. Based on those precedents, Soos combined cinchona alkaloids with thioureas for the enantioselective 1,4 addition of nitromethane to enones, obtaining enantioselectivities up to 98%. As in previous examples, the chiral tertiary amine activates the nucleophile, in this case the nitronate, while the thiourea binds the enon, increasing its electrophilicity. In 2005, Commun used the Soos catalyst in the Michael addition of malonates to nitroalkenes, demonstrating higher performance than Takemoto's thiourea, even when using lower catalyst loadings. Chiral tertiary amines containing thiourea moieties have been the inspiration for many other organocatalysts by modifying the hydrogen donor, such as bifunctional squaramides, ureas, or sulfonamides. However, in most cases, the character of the basic active site is similar to Takemoto's or Soos catalyst. In order to increase the diversity of the active site, several authors have developed bifunctional catalysts based on nitrogen and phosphorus-containing bases, such as guanidines or iminophosphorins. All those Bronsted bases are more basic than tertiary amines, allowing faster reaction and unlocking new reactivity. First, we will go through nitrogen-containing bases, like guanidines and cyclopropenimines. In 1999, Corey reported the enantioselective cyanation of imines using hydrogen cyanide as the cyanide source. Despite the structural simplicity of the catalyst, the interactions with the substrate were maximized, affording high enantiocontrol. First, the catalyst is protonated by the hydrogen cyanide, releasing the cyanide anion as the nucleophile. Then, the protonated guanidine activates the imine by hydrogen bonding with the NH group, while the phenyl rings in the catalyst and substrate interact through p-stacking, exposing the less hindered phase. 2 years later, Ishikawa reported the use of exocyclic guanidines as catalysts for the enantioselective 1,4 addition of glycine esters to acrylate derivatives. In this case, the hydrogen donor activating the electrophile is the alcohol present in the catalyst. Based on Ishikawa's work, Lambert and co-workers reported in 2012 the use of chiral cyclopropenimines, using again a chiral alcohol derived from phenylalanine as the key enantioselectivity inducing moiety. The increased basicity of Lambert cyclopropenimines with respect to chiral guanidines allowed a remarkable decrease on the catalyst loading and reaction times, while increasing the enantioselectivity up to 99% EE. Moving to phosphorus-containing chiral Bronsted bases, the most relevant examples are iminophosphorins and phosphacins. In 2013, Dixon reported the synthesis of chiral iminophosphorins as a new group of efficient catalysts for the Asymmetric reaction. The overall catalyst design combines a thiourea moiety as a hydrogen donor for activating the imine, while a strong base catalyzes the formation of a nitronate. The anti-selectivity of the reaction is controlled by the high bulkiness of the protecting group on the imine and the terbutyl moiety in the chiral catalyst, favoring the attack through the C phase. This combination afforded the product with excellent anti-selectivity. On the other hand, Oil reported in 2007 the use of a highly basic chiral phosphacene for the anti-selective addition of nitroalkanes to aldehydes. In this case, the active phosphacene is formed in situ by treating the precatalyst with a base. The NH groups in the catalyst have a double role in the reaction. First, they act as stabilizers for the nitronate, while the proton coming from the nitroalkane acts as a weak Bronsted acid to activate the aldehyde. This activation mode is similar to the one shown for Corey's chiral guanidines. The third block of non-covalent chiral organocatalysts are known as anion binding catalysts. This type of catalyst might be confusing due to the structural similarities with some bifunctional Bronsted bases, like Takemoto's thiourea. In fact, some early examples proposed bifunctional Bronsted base type mechanisms that have been corrected years later. As we will see, the thiourea moiety plays a different role in this case. One of the early examples was reported in 1998 by Jacobsen. When analyzing the mechanism in detail, they found no direct interaction between the thiourea moiety and the imine. Based on mechanistic studies, the thiourea reacts with hydrogen cyanide to form the stereomeric intermediates, stabilizing the cyanide anion by multiple non-covalent interactions. The key factor controlling the anti-selectivity is the imine stabilization by the protonated shift base. In the following slides, we will go through some representative examples of this type of catalysis, where the Jacobsen group made great contributions. For instance, in 2004, they proposed an anion binding catalysis for the acyl-Pictet-Spengler reaction. The initial reaction between an acyl chloride and the imine might form the corresponding alpha-chloroamide. Also, the thiourea catalyst can activate the carbonyl group through hydrogen bonding. SN2 mechanism does not explain the origin of the anti-selectivity. Therefore, the most plausible reaction pathway involves the formation of N-acyliminium ion as a prochiral species for the Pictet-Spengler reaction. The proposed activation mode involves a stabilization of the acyliminium ion by the thiourea binding anion. In contrast to the Bronsted-based catalyst, where the basic nitrogen is crucial, in this proposal, the pyrrole moiety has limited basicity, and its influence on the anti-selectivity is mostly steric. Another closely related example was reported in 2007 by Takemoto, using quinolines as electrophiles. Similar to the previous example, the initial step involves the formation of the corresponding acyl-quinolinium ions. On the other hand, the boronic acid is expected to interact with the primary alcohol in the chiral thiourea. Also, the authors suggested a direct hydrogen bonding activation of the carbonyl group by the thiourea moiety. This proposal does not explain the role of the chlorine anion. More recent studies have proposed an alternative pathway where the thiourea stabilizes the acyl-quinolinium ion by binding the chlorine anion. A year later, Jacobsen reported the thiourea mediated an anti-selective addition to chloroisochromene derivatives, using in this case silylenol ethers as nucleophiles. As in the previous examples, the equilibrium between chloroisochromene derivatives and oxocarbenium ions is key to understand the origin and the enantiomer control. Based on this catalyst, they also develop a more complex catalyst containing two thiourea moieties. The supramolecular interactions between both thioureas and the chlorine have a drastic effect on the reactivity, allowing 100 times lower catalyst loading, shorter reaction times, and higher reaction concentration without losing selectivity. In previous examples, the anion was a mere spectator, contributing to the stabilization of the corresponding cation. However, the anion binding catalysis has also been applied to more complex reactions, where the anion has an active role in the reactivity, similar to the asymmetric cyanation reported by Jacobsen in 1998. A similar example was reported by Jacobsen and co-workers in 2009 to afford alpha-chloroamines. Initially, the catalyst binds the chlorine anion and the acidic proton. Then the phosphonium ion acts as a Bronsted acid, activating the acidity and controlling the selectivity. Unlike in previous examples, the chlorine anion is used as the nucleophile for the ring opening reaction. On the other hand, non-thiourea-based catalysts have also been developed in this field. A representative example was described in 2011 by Oe and co-workers and applied to the alpha-alkylation of oxindoles. In this case, the anion is bounded by an amide and a triazole, easily synthesized through click chemistry. Another difference with previously shown examples is the proposed reaction mechanism. Although similar examples involving the formation of secondary and tertiary carbocations have been reported, the lower stability of primary carbocations suggests an essential reaction mechanism for this case. Taking advantage of the simplicity to access chiral triazoles, the Garcia-Manceño group developed a tetratriazole containing catalyst. In this case, the stabilization of the anion by chiral catalyst happens only via hydrogen bonding with triazole and aromatic protons. This anion binding catalyst demonstrated high selectivity in the enantioselective functionalization of quinolines, complementing thiourea-based chiral catalysts. We are moving now to the last group of catalysts selected for this episode. Over the last 2 decades, chiral Bronsted acids have become some of the most widely used and versatile chiral organocatalysts. The first examples in the field were independently reported by Terada and Akiyama in 2004 to perform enantioselective additions to imines. Terada and co-workers use a bienol-derived chiral phosphoric acid to catalyze the addition of dicarbonyl compounds to imines. The proposed mechanism consists of a bifunctional activation of the imine, while the OH group of the phosphoric acid acts as a Bronsted acid, increasing the reactivity of the imine. The phosphoryl group stabilizes the enol form of the dicarbonyl compound as nucleophiles. The enantiocontrol control is mainly directed by the substituents in position 3 of the bienol. On the other hand, Akiyama used a chiral phosphoric acid on the enantioselective Mukayama-Mannich reaction. In this case, an imine containing a phenol moiety was selected, and a bidentate interaction between the imine and the phosphoric acid is proposed. 2 years later, Lees reported a cooperative catalysis combining chiral phosphoric acids and morpholine. This combination allows selective transfer hydrogenations of alpha, beta, and saturated aldehydes using Hans esters as the hydrogen source. The iminium ion catalysis activates the aldehyde, while the chiral counter anion controls the hydrogen transfer in a chiral environment. This type of catalysis is also known as chiral anion or chiral counter anion directed catalysis. Also, the examples of chiral Bronsted acids shown until now use bienol as the chiral scaffold. Several diols have been used for analogous reactions. The most relevant ones are octahydrobienol, spinol, or sphenol. The main difference between those scaffolds are the bite angle and the solubility of the phosphoric acid. On the other hand, tuning the substituents on the chiral diol allows controlling the steric effects, or the electronic demand of the catalyst, maximizing the catalyst activity and the enantiocontrol control. Another strategy to increase the versatility of chiral Bronsted acids is the modification of the acidity. In 2006, Yamamoto reported an enantioselective Thiel-Salder reaction using Bronsted acid catalysis. Since mildly acidic phosphoric acid did not catalyze the reaction, they developed entry-fluid phosphoramides as more active catalysts. Using bulky substituents close to the active site was found crucial for the reactivity, since less sterically hindered catalysts suffered from deactivation by cerylation of the phosphoramide. This type of catalyst might also act as chiral Lewis acid under certain conditions. In 2010, the same group reported another reaction involving silyl enol ethers. More detailed mechanistic studies show different reaction pathways depending on reaction conditions. At low temperatures, the catalyst acts as a Bronsted acid. This activity was confirmed by adding diterbutylpyridine, which is known to inhibit any potential Bronsted acid catalysis. However, when warming up the reaction to room temperature, the reaction proceeded even in the presence of a Bronsted acid blocking reagent, suggesting a different reaction pathway as a chiral Lewis acid. Since Yamamoto's report, several chiral Bronsted acids have been developed, focusing on the modification of the Bronsted acid moiety and establishing a direct relationship between the acidity and the catalytic activity. While mildly acidic catalysts as chiral phosphoric acids are mostly used as a chiral Bronsted acids, highly acidic organocatalysts can also be used as chiral Lewis acids under certain reaction conditions. For instance, in 2009 and 2012, Lees reported the synthesis of chiral disulfonamides and imidophosphoric acid respectively. Chiral disulfonamides, also known as DSI, were first applied to the enantioselective Mukayama-Aldol reaction. The proposed reaction mechanism consists of an initial silylation of the Bronsted acid. The high lability of trimethylsilyl group allows using it as a chiral Lewis acid, activating the aldehyde, while the chiral anion modulates the enantiomer control. A few years later, Lee described an enantioselective Friedel-Crafts reaction of indoles and N-sulfonylamines using DSI catalyst, demonstrating the applicability of this type of catalyst as a purely Bronsted acid. The proposed activation mode is closely related to the one previously reported for chiral phosphoric acids. On the other hand, List applied imidophosphoric acids to the asymmetric synthesis of acetals through intramolecular 1,2 addition of primary alcohols. Thanks to the sterically confined active site, ITP catalysts afford high enantioselectivity, while other chiral phosphoric acids were unsuccessful. However, a smaller cavity for the active site, along with relatively low acidity, also limits the applicability of ITP catalysts to broad range of reactions and substrates. A few years later, List and co-workers combined the confined active site from ITP catalyst and the higher reactivity of disulfonamides, resulting in a new type of chiral Bronsted acid, chiral imidodiphosphorimidades. These catalysts have mostly been used in reactions involving silylated reagents such as the Hosomi-Sakurai reaction. In a similar way to DSI catalysts, a labile silyl group acts as a Lewis acid activating the aldehyde, while the chiral anion directs the enantioselectivity. However, as one of the most promising Bronsted acid catalysts of the last years, a few examples confirming their activity as Bronsted acids have also been reported. In this case, the acidification of an alkene yields a tertiary carbocation, which is then trapped with the alcohol to afford cyclic ethers in enantiomeric excesses up to 97%. With this, the second episode of this course about asymmetric organocatalysis comes to an end. Thank you for watching.
Thank you, Aitor, for the wonderful introduction to organocatalysis. If you'd like to learn more, please visit the listed references, and if you enjoyed this episode, please like and subscribe. Thank you for watching.